क्या बात है, बहुत कम लोग ज्वाइन किए अभी तक।
गुड आफ्टरनून सर।
फ्रेंड्स आ रहे हैं बाकी?
सर आई गेस सर मैंने मैसेज डाल दिया था बट आई डोंट थिंक सो।
चलो
आ
थोड़ा
रहे होंगे सर धीरे धीरे।
एक्सप्लेन कर देता हूँ। आई विल एक्सप्लेन है ना, बिकॉज इट इज ऑलरेडी वेरी देयर। जस्ट एक्सप्लेन लिटिल बिट है ना, जल्दी छोड़ दूंगा आपको।
ओके सर।
So we have studied the basic rules of the transport phenomena for the momentum transport. है ना? So what are the basic rules for the momentum transport? It depends upon the two axiom. Axiom one, which said that mass is conserved, and if you are saying that mass is conserved, that means mass cannot be created, cannot be destroyed. And when you apply this return this statement in the mathematical form, you will end up with the equation of continuity. So these are the equation of continuity in the vector tensor form, and then you have the expandation of the equation of continuity in the different coordinate system. Okay, so in the standard form, we are using the three coordinate system: Cartesian, cylindrical, and the spherical coordinate system. So we have the units, the vector and tensor, that the equation of continuity in the all three coordinate system. If fluid is incompressible for liquids, we have the another form of equation of continuity. That is the del dot V equal to 0. You may have the expansion of this equation in the vector and tensor form. Okay. Then axiom 2, that tells you that the momentum is conserved. Momentum is conserved is equivalent to, this statement is equivalent to the second law of second Newton's law, and F equal to ma basically. So here basically you are adding all the forces and all the momentum. In the fluid mechanics, when your phase is fluid, in the fluid phase, then the momentum comes with the fluid. The fluid flows, so that fluid has some velocity, some moment, and mass that is equivalent to the momentum. Then when the fluid leaves from the system, that also takes some momentum with it. Okay, and then you have the number of forces, different type of forces, which will add up, and that should be equal to rate of accumulation of momentum in the control volume. Okay. Now, because here you have to acknowledge all the forces. So there are two types of forces: body force and surface force. What are the body force? Which apply on the whole body. It depends upon volume and the mass of the system, like gravity. Okay, and what are the surface forces? Surface forces does not depend upon the mass, it depends upon the surfaces. Okay, like pressure force and shear force. Okay, so the pressure force that acts on the normal direction, it is a compressive force. It is always acts in the inward direction of the surface. Okay, and what is the shear force? Shear force is a friction force. You know, so when you calculate the friction force at every surface, there are three possible direction of the friction force. Okay, so we have written in the x directed surface you have tau xx, tau xy, tau xz. That is the x directed forces. Tau yx, tau yy, tau yz. That is the y directed forces. Tau zx, tau zy, and tau zz. That is the z directed forces. Okay, so you have the three different direction of the forces each at every surfaces. Okay, the total components are 9. Okay, now we will start with the problem. Now we will start the actual problems related to the transport phenomena. How to solve? Okay, so because we have studied the two axioms, so now we will start with the momentum transport problems. Tomorrow we have the one class from, what is the, कितने बजे का क्लास?
सर एक मिनट में देख के बताता हूँ।
तुम्हें बताओ।
सर कल है। सर कल हमारी क्लास है 1 से 2।
एक से दो है ना, ठीक है, तो कल पूरा हो जाएगा। Okay, so I will give you the brief introduction to what is the momentum transport problems. Okay, so in the transport phenomena, there are three different types of transport: momentum transport, heat transport, and mass transport. Okay, here we will start with the momentum transport problems. Okay, so what are the momentum transport problems? Basically, this is the fluid mechanics problem. Okay, so in actual, whenever the fluid flows in a open channel or in a closed channel, okay, so there is always a driving force. The driving force is either the pressure difference, or gravity, or you have the shear force. Okay, so due to this forces, fluid flows from one point to another point. So what you have to do, you have to correlate the forces and the velocity, or the mass flow rate, or the flow rate of the fluid. Okay, basically for a different type of problems, like flow inside a pipeline, like flow on a entangled plane, or like flow inside a circular in a cylindrical structure, or like flow in a canal, है ना? So these all are the types of flow. Okay, so in these different types of flow, you have to correlate how the forces, if the pressure drop, if the pressure difference between 2 points are like 4 bar, so what should be the velocity of the fluid, that you have to calculate. Now, how much force is required for the transport, and that for the flux. So flux is here momentum transport. Okay, so the fluid transferred from one point to other point. So how much pressure force, or how much gravity, or how much shear force is required, that you have to calculate. And then you have to, I have already told you in the velocity that in the fluid mechanics there are different types of velocity. One is the linear velocity, one is the average velocity. So in the linear velocity, you have the local linear velocities. So you have to calculate the velocity at each point, that you have to calculate. Okay, at every point you have to calculate the velocities. Okay, for that we have to do the momentum balances based on these two principles. Okay, we will calculate this based on these two principles. First is the mass is conserved, second is the momentum is conserved. We use this basic principle and then derive the expression, design equation, which tells you what will be the velocities or the flow rate with respect to the forces, pressure drops, gravity or shear forces. So whatever the centrifugal forces, whatever the forces you are applied, so on of that, for how much velocity you will get for a particular fluid. Okay, so you can solve any problem. Suppose you want to solve what is the force, drag force will be applied on the aeroplane, that you want to calculate, or how much, what should be the velocity of the aeroplane for the takeoff, what is the takeover velocity of the aeroplane, that you have to you want to calculate, or you want to calculate that what is the velocity inside a pipeline of the fluid, and when the pressure drop is given P1 or P2. Or if you want to calculate, suppose there is a building, long building, and air is moving in a cyclone. During the cyclone, what is the, how much force is applied due to air movement? Okay, that you want to calculate. So each type of problem you can solve by using these two basic principles. Okay, only these two basic principles are required for solving every type of problem. But the solution, the equation which will be derived, that will be very complex equation based on the problem. And if you are solving the aeroplane problem, the equations will be very difficult to solve. And these equations require the computational fluid dynamics, which is a higher level course. Okay, the procedure will be same, which you will use here. The procedure will be same. Once you understand the procedure, you can solve every problem. Until the basic requirement is the mathematics. And you should know the mathematics, how to solve the higher order differential equations, partial differential equations. And if you know how to solve the higher order partial differential equations, you can solve any type of problem. Okay, so this is a basic subject, transport phenomena. Here we understand the process. First we will understand the process, and we will solve the problem which are easy to solve using the paper and pen. which can be solved within 15 minutes, 20 minutes, or half an hour time duration. If you solve more complex problem, turbulence problem, when you have the turbulence flow, because solution of the laminar flow is very easy. When you use the laminar flow, solution will be very easy. When you use the turbulent flow, solution will be very difficult. Okay, so we will solve only the laminar flow problem. Although you can solve turbulent by using the same procedure, you can solve turbulent flow problem also, but that required the more computational power. You need the more complex mathematics. You need the solution of that mathematics that is only possible by using some computational methods. Okay, so in this subject we will solve the easy problems. Okay, so first problem which we will solve is the flow through the horizontal circular pipe. Flow through circular tubes. Okay, so when fluid flows in a, this is a very common problem, especially in the chemical engineering, when you want to transport the fluid from one point to other point inside the plant or outside the plant. Like that, the crude oil. Crude oil is transported from one city to another city, or the diesel fuels like diesel, petrol. They are transported from the one city to another city by using the pipelines. Okay, this is a very basic problem where fluid is flowing inside the tube, and you want to calculate what is the velocity of the fluid based on the pressure, or how much pressure is required for getting a given flow rate. Okay, so I am making the problem I am making a problem which is very easy to solve. Okay, so the problem is, consider an incompressible Newtonian fluid flowing through a horizontal pipeline. Pipeline or tube. Okay, assume that fluid is in laminar flow. Reason: fluid flow is laminar and under steady state conditions. Determine the velocity profile and average velocity of the fluid. Okay, so this is the problem. You have a incompressible fluid, that means liquid. Incompressible fluids means pressure is constant, means density is constant. Density does not depend upon the position or time. Okay, so that is the incompressible fluid. Newtonian fluid means fluid obeys the Newton's law. You can apply the Newton's law in this case. Okay, that is flowing inside a horizontal tube line. Okay, so there is a tube or the pipeline. So the first task which you have to do when you have the momentum transport problem or any transport problem, you have to make the diagram of the problem. Okay. So you should understand this process. Once you understand this process, you can solve any, you need not to remember any derivation. You can derive any equation, any design problem. You can solve any design problem without remembering it. Okay, you need not to remember or mug it. You have to just understand the procedure. Once you understand the procedure, you can solve the problem. So this is the pipeline. Suppose the length is L. So first thing which you have to do after reading the problem, you have to draw the diagram of the system. That is the first requirement. Once you draw the diagram of the system, then only you can understand the problem. Okay. First, draw the diagram very correctly. Okay, so this is the diagram of the system. You have a horizontal pipeline where fluid is flowing in one direction. Suppose fluid is flowing in this direction. This is the central line. So here fluid is flowing in this direction. Okay. So because it is a horizontal pipeline, so fluid will flow due to the pressure drop only. So there should be a pressure drop. Okay. If there is no pressure drop, then the velocity will be zero. Okay. For flow, you need the driving force. What are the driving force in the momentum transport, in the fluid mechanics? Pressure drop, gravity, and the shear force. Okay, so there are three different types of driving force in the momentum transport. Fluid will either flow due to the pressure drop. If you maintain the pressure difference between 2 points, then the liquid will flow in the from higher pressure to the lower pressure. That is one thing, है ना? At one place you have the higher pressure, at other place you have the lower pressure, then the fluid will flow from higher pressure to the lower pressure. If there is a gravity force applied, if fluid is present at higher position, then that may flow due to the gravity from high point to the low point. In this case, because the pipeline is horizontal, so you cannot assume the gravity. And the gravity you can include the gravity if pipeline is vertical. Okay, if the pipeline is vertical, then gravity will also responsible for the flow. But this is a horizontal pipeline. In the horizontal direction, you don't have any gravity for flow. Okay. Third thing is shear force. How the shear force is how the shear force may work as a driving force. Suppose you have a belt. This is a belt. This belt is situated inside a pipe, inside a liquid fluid. This belt is situated inside a liquid fluid. Now, suppose this belt is moving in one direction with velocity v. This is a belt, solid belt, that is moving in one direction with velocity v. So there is a friction between the solid body and the liquid body at the surface, and so it will drag some of the liquid with it. So that is the transportation of fluid due to the this is the transportation of fluid due to the shear force, due to the friction. When the solid body is moving, so it will take, due to the friction, it will take some of the liquid with it. So that is the transportation due to the shear force. Okay, so you have the three main reasons for the driving force for the transportation in the momentum transport: pressure drop, gravity, and shear force. You may also have the centrifugal force, but we will not discuss the problem related to the centrifugal force in this subject, and that we will discuss in the different subject. Okay, here we will discuss about the pressure force, about the gravity force, and about the shear force. Okay, so I am explaining you the process. First, you should understand the process, then we will solve the complete problem. So, first thing which you have to do when you make the when you read the problem, you have to make the diagram. Okay, first thing you have to make the diagram. You made the diagram. This is the circular pipe where the fluid is flowing from this point to this point. The length of the pipe is L. The diameter of the radius of the pipe is suppose R, capital R. The pressure drop between at the both ends of the pipe is P1 and minus P2 minus P1. This is the final pressure. This is the initial pressure. And this is the pressure drop in the pipeline. Okay, that's why the fluid is flowing in this direction. Okay, now once you make the diagram, then the second thing which you have to do, you have to put the coordinate system. Okay, so after making the diagram, you have the second point is important point is you have to put the coordinate system. Okay, so how to put the coordinate system? There are rules for which you there are some points which you have to understand and which you have to remember. First thing, you have to put the coordinate system which is related to that system geometry. Okay, if system geometry is rectangular, if your system geometry is rectangular, then you have to use the Cartesian coordinate system. If your system geometry is circular, cylindrical, if your system geometry, three-dimensional system geometry is cylindrical, then you have to use the cylindrical coordinate system. If your system geometry is spherical, then you have to use the spherical coordinate system. So first thing which you have to understand, you have to select the coordinate system based on your system boundaries, system diagram, okay, or system geometry. So your system geometry is cylindrical in this case, so you have to select the cylindrical coordinate system. So now select the cylindrical coordinate system. So that is the r, theta, z. Cylindrical coordinate system is coordinates are r, theta, and z. These are the cylindrical coordinates. Now you have to put the cylindrical coordinate system on the diagram. Where is the origin? You have studied the coordinate geometry. Everyone has studied the coordinate geometry. So here we are using the coordinate geometry only. We have to put the put the coordinates in the actual diagram so that we can solve the problem easily. Okay. So what we have to understand that here we have to make the symmetry in the diagram. So the diagram will become symmetrical. Then only we can solve the problem easily. Suppose you put the coordinate here. This is r, this is z direction, this is r direction, this is theta direction. So what will happen? Your velocity at this point, velocity will become the, what is the direction of velocity here? Here velocity is the z direction, that may depend upon r direction also and theta direction also. Okay, so you have to make the diagram, put the coordinate system in such a way that it will become the symmetrical. Okay, so that you can solve the problem easily. The most symmetrical way to plot the put the coordinate system in this case is use the center. Use the initial point. This is the origin. This is the initial point of the system. Put it as the origin. O is the origin. The axis, the central axis of the pipeline is the z-axis. The radial direction of pipeline is the r-axis. And this circular direction is the theta axis. This is the simplest way to put the coordinate system in the pipe flow problem. Okay, r, theta, z. Okay. So the most important point is you have to substitute the coordinate system, accurate coordinate system on the diagram. That is the axial axis is z, radial axis is r, and circular direction you have the theta coordinate. Okay, so z, r, theta. These are the accurate coordinate system. Okay. Now, once you substitute, you have done the both things. You have make the diagram. Second point, you have to put the accurate coordinate system at the exact point and the accurate point. You can also use this as a z-axis. But if you use this as a z-axis, then r-axis is not symmetrical. And in this direction you have the positive r, in this direction you have the negative r. So here the boundaries are very clear. Okay, now the boundaries are very clear. This point and this point should be equal. And if you take the middle point as a z-axis, then you have the symmetry in the diagram. Okay, so you have to remember this. If you are deriving any design equation for different type of system, you have to use the same thing. Okay, now this is the second point. Put the coordinate system. Now the third point. So what we are doing here, we are deriving the equations which correlate the velocity or flow rate to the pressure drop. And if you are applying P1 minus P2 equal to 10 bar, the length is 10 meters. So what will be the velocity of fluid which that you are going to calculate in this question? Okay, so you are deriving a equation, a formula that is called the mathematical model. Okay, so every mathematical model, every mathematical physical formula which you are using, that depends upon, that will be derived by using some assumptions. And the mathematical modeling is you are mimicking the physical, the nature in the mathematical form, and you are predicting the future. If you are applying the this much of pressure drop, what will be the flow rate? You are predicting the future based on some you are predicting the future, or you are mimicking the nature. You are mimicking the nature. So you cannot mimic the nature, or you cannot predict the future with 100% of accuracy. For that you need some assumptions. That assumptions makes the problem easier to solve. It is it is very difficult to solve the problem, any natural problem. You can derive the equation, but that equation will so complex you cannot solve that problem 100% accurately. Even for the simple problem also, for the pipe flow problem also, and it is very difficult to know the velocity at each and every point with 100% accuracy. That is not possible. You cannot mimic the nature with the 100% of accuracy, or you can say 100% accuracy is not a feasible quantity when you are mimicking the nature. You have to take some assumptions, so that assumptions will make the problem easy to solve. There might be plus minus 2%, plus minus 3% error with the actual condition, that you can take as a design error. And so what we will do, we will derive the equation, use that equation to solve the problem, actual problem in industry. So we know that that equation has the plus minus 3% of error. Okay, suppose your pressure, the pressure required comes as a 2 bar. So what you will do, you will add plus 3% in 2 bar. Okay, that will become your, this will become your design error. In other words, you will add the design error in actual quantity, and you will design the system based on this 2 plus the 2 bar plus 3%. That you will use, this quantity you will use for the designing purpose, and because you know that your design equation has the 3% of error. Okay, so you can use the, you can over design your system of that error, and so that is very easy way to overcome the different errors comes in during the modeling part. Okay, so whenever you derive a equation, remember any you mathematically you cannot mimic the nature 100% accuracy accurately. So you have to take the assumptions. So here we will take the third step. You have to write the assumptions. Why it is required writing the assumptions? Because based on assumption only you are deriving the equations. Okay, so you know your assumption is valid or not, and how much error will come due to every assumption. Sometimes these assumptions are totally wrong, then you have to drop out that assumption. Okay, so you have to first, you have to take the assumptions. So first assumption is, which we will take in solving this problem, it is given in the problem only. You have the incompressible fluid, Newtonian fluid. That means incompressible Newtonian means your density and viscosity are constant. Fluid density and viscosity are constant. That is the first assumption. Second assumption which we have to take is system is in steady state. This is the second assumption, that your system is in steady state. So there, what is the meaning of the steady state? It is given in the problem. And it is given in the problem that your system is in steady condition. So what is the meaning of steady state? Anyone? What is the meaning of steady state?
Sir, equilibrium.
It is not the equilibrium. You can say the equilibrium, but here it is not the equilibrium. Equilibrium means
Sir, I guess in a stable way so that sir उसमें कोई disturbance ना हो.
हाँ मैं बताता हूँ steady state का मतलब क्या है. Basically, when in the reaction engineering, you can assume that steady state means the equilibrium, but steady state means not equilibrium. Steady state means the quantities which you are studying, and the physical quantities which you are studying is not changing with time. Okay, so steady state means the quantities or the parameters are constant with time. Now why it is an important condition, and why we are taking this? First thing, why we are taking this? Okay, so suppose you have two tanks, two large tanks. Okay, now you have to transport this tank. The capacity of each tank is 50,000 meter cube. Okay. Now you have to transport the liquid from this tank to the another tank. Now you have to transport the liquid from the first tank to the second tank. Okay, what you can do? You can use a pump to flow the fluid from one point to the other point. Okay. Now when you start the pump, within 10 seconds you will achieve a flow rate V. The V1 is the flow rate, average flow rate or average velocity, or Q1 is the volumetric flow rate which you will achieve after a constant time 10 seconds. Okay. Then for 1 hour, 2 hour, whatever the time required to flow to empty this tank and to fill this tank, at that whole time the velocity or the volumetric flow rate that will remain constant. Okay. In chemical engineering, most of the processes are the steady state continuous processes. Continuous process means, suppose this is a reactor. So most of the reactors are continuous reactor. Continuous reactor means the temperature. In this reactor, you maintain the temperature T1, a constant temperature, a constant pressure, sorry, a constant concentration, a constant pH. You maintain all the conditions in the reactor. The reactant continuously enter in the system and product continuously leaving from the system. So the concentration of reactant at the entry point, that is constant. Suppose this is the C0. The flow rate of reactant, that is also constant, Q1. The concentration of the product will be constant. Suppose C2. The flow rate of products are also constant, Q2. So this reactor will work continuously for 24 hours per day, for 7 days per week, for 330 days or 330 to 340 days per year. You will only stop the reactor for 1 month or for 20 days for the maintenance purpose. Otherwise, this reactor will work continuously for 24 hours, for 7 days a week, and for 330 to 340 days. Why? Because it is required. If you want to work in the batch process means you fill the reactor. What is the batch process? Batch process means you fill the reactor, do the reaction, then takes the product out from the system. If you work in the batch process, then initially the temperature is 25 degrees Celsius. You have to increase the temperature, suppose to 50 degrees Celsius. Then you have to reduce the temperature. So in this process, a lot of energy will be Tested out because you have to first increase the temperature of the system, then reduce the temperature of the system. Okay, here you have to maintain the temperature. You have to maintain a constant temperature, constant concentration, constant pressure in a reactor. That is much easier and much effective way for a reaction. Okay, or for any process, not reaction only, for any process, for separation process also, even for mechanical processes also. So this is called a steady state continuous process. Steady state means the temperature, concentration, pressure, anything, flow rate, any quantity which you are studying, that is not changing with time. That is constant with time. That is called the steady state. Now you understand what is the steady state? Steady state is means parameters are constant with time, and the
Yes, sir.
means in this equation, which you have studied the equation, in this equation, dρ by dt, this is the change of density with time. This will be zero. And the time के साथ now the velocity density will not change with time because we assume the steady state. Okay, this is the most generalized equation. This equation is true for steady state also and steady state also. We will only solve the problem for steady state. If required, you can solve for a steady state also, but here we will solve for steady state because in longer period, most of the processes which occurs in the industry, they are the steady state processes. Third, first is assumption we have taken density and viscosity are constant. That means this problem is solved for the simple liquid fluids. Simple liquid fluids like water, oils, these are the simple liquid fluids for which we are solving this problem. Okay, so water and oils are the major fluids which used in water. There are all solvents come under the water only. So these are the major fluids. Now the third thing, laminar flow. This is also very important. You may have the laminar flow. So in this case, we take the laminar flow as the assumption. Why? Because if you use the turbulent flow, then the problem will become very complex. You cannot solve the turbulent flow problem by using simple pen and paper. You need the computational power to solve. That we will discuss later. Why we require the laminar flow assumption. Okay, so we assume the laminar flow. Fourth assumption which we have to take here is the Newton's law of viscosity is applicable. There are two different types of fluids, Newtonian fluids and non-Newtonian fluids. Newtonian fluids are the fluids which obey the Newton's law of viscosity. Non-Newtonian fluids are the fluids which do not obey the Newton's law of viscosity. So here we assume that Newton's law of viscosity is applicable. Fifth is fully developed flow. Okay, so we will start with fluid density and viscosity are constant, system is in steady state, laminar flow, Newton's law of viscosity is applicable, fully developed flow. These are the 5 assumptions which we need to take for solving this problem. After taking these 5 assumptions only, we can derive the equation by using the simple pen and paper. And the problem will become easy enough to solve using the pen and paper, using the simple mathematics. Otherwise, you have to go for the numerical methods. Okay. So what is the mean of the fully developed flow? I have already told you the fully developed flow and the developing flow. Boundary conditions, you have studied the boundary conditions in the previous classes. So Basically, whenever the fluid comes with the contact in the whenever the flowing fluids comes with the contact of a solid surface, the adjacent layer, the flow of the adjacent layer the flow of the become same as the velocity of the solid body. Okay, so that is called the no slip boundary condition. That is also also assumption here, and the no slip boundary condition is applicable. Okay, so whenever the fluid comes to contact a solid body, due to the friction, the adjacent layer, the velocity of the adjacent layer will become the same as the velocity of the solid surface. So this is, in this case, your solid surface is tube. So the tube velocity is zero. Tube is in the stationary condition. So the tube velocity V is zero. So the adjacent layer velocity, the fluid which comes to the contact with this tube, the velocity of that layer is also zero. Okay. Now that layer will drag the another fluid layer. So fluid is flowing in the layers. Okay. So that layer will drag the another layer. That will drag the another layer. So there is a velocity profile at the end. Okay, so here the velocity is developing, and the drag, due to this drag, velocity is developing, and after some time, both this is called the area or the region where the solid body has the effect on the flowing fluid, that is called the boundary layer, and where the thickness of boundary layer is increasing, that is called the developing boundary layer. So what will happen? I am making the big diagram. Okay, so suppose this is your tube. This is your tube. This is central axis. So here velocity is zero, v is zero. So the next layer velocity will be zero. Next layer there is some velocity. So you will have the area region where because there is a difference between the time. So this layer will drag the another layer, this layer will drag the another layer, then the another layer will drag the another layer. So you have the region where you have the developing boundary layer. So this is called the boundary layers, and you have the region where you have the developing boundary layer. This is the developing boundary layer. When the both boundary layers merges, you have the fully developed region. This is the fully developed region. And this is the developing region. Okay, so when you have the developing region, then the solving the problem, momentum transport problem for developing region is slightly difficult. Why? Because in this case, suppose this is the velocity v. So velocity v, this is the z axis, this is r axis, and this is theta axis. So in the developing region, you have the vz, non-zero velocity component vz, that will depend upon r, as well as that will depend upon z, because when you move in this direction, velocity is changing. And here you have the high velocity. Once you come in this region where you have the effect of the solid body, the velocity will reduce. Okay, so in the z direction also velocity is changing. In the r direction you have the solid body. Here you have the no effect on the solid body. In the r direction also the velocity is changing. So you have the partial differential equation Vz divided by del r plus del Vz by del z. That will be difficult to solve. Okay, in the fully developed region, you have the velocity which will depend upon r direction only. So here you have the Vz which will depend upon r direction only. Then you have the dVz by dr only. Single order differential equation, fully developed total differential equation. Okay, in this case the problem is easier to solve because ordinary differential equations are easier to solve. So what we will do, we will solve the problem for only fully developed region. Okay, so the assumption is, if your length is very long, if the length of the pipe is very long, means suppose L by D, L is length of the pipe, D is diameter of the pipe. If L by D is greater than 50, length of the pipe is 50 times higher greater than the diameter of the pipe, then you can neglect then developing region can be neglected. Okay, so here you can neglect the developing region because L by D is greater than 50. Okay, so this part is very small than this part. You know, the developing region is very small in comparison to the whole length of the pipeline. So you can neglect it easily. Okay, समझ में आ गया? No slip boundary condition. I have already told you what is the no slip boundary condition. This is the part where the velocity, whenever the flowing fluid comes into the contact with the solid body, the velocity of the adjacent layer, which is comes to the contact with the solid body, the layer, that velocity of that layer is the same as the velocity of the solid surface. Okay, that is called the no slip boundary condition. That means there is no slip between the fluid and the solid part body. Okay, solid and solid body and the fluid will become locked together. Okay, that is called the no slip boundary condition. Okay, so we will take the no slip boundary condition as the assumption. Okay, so we will solve this problem tomorrow in tomorrow class. Okay, this is the assumption. Now we will in tomorrow class we will solve the problem.
All right, sir.
चलो ठीक है.
Thank you, sir.
हाँ, किसी को पूछना है
Thank you,
यहाँ
sir.
तक?
Sorry, sir.
कुछ पूछना है आप लोगों को? Any question?